Hello, everybody, and welcome back again in our session number 4. In this video, we are going to talk about the elastic and inelastic serviceability analysis based on wind load and seismic and by inserting node combinations. Today, we have to talk about the deflection of the slab, the sway, and the drift for elastic and inelastic analysis. Here our ETAS model that we have been designed for, and we have been modeled this in the previous session, and we are going to know how to define the load patterns for the earthquake, seismic, and for the wind load. Here's the option define. Go to load pattern. We have dead load, which is on weight. We have live load, which has a preposted load. Okay. So now we are going to talk about the seismic or the wind first. Wind load, and there's a wind here. Okay, and we'll use UVC. There's no UVC here, so maybe you can use any code you want. Maybe we'll use the Euro code. Here's Euro code. Okay, and add a new node. Then you are going to use seismic and EQX. Seismic, and we use also the code that you are familiar with. For example, Euro code 8. EQY. So we have EQX, we have EQY, we have point load. So for modifying, we will need to modify the little bit. Here's the exposure extent of diaphragm. We have by default wind load coefficient, we have the load coefficient, wind velocity based on the building location, which is based on your location. So you can put 60 meters per second. The terrain based on occupancy. This you need to go return to your own code when you are going to design. And there's exposure height. What is exposure height? Of course, starting from the top until the bottom story, which is the bottom story. Of course, will not be the base. It will be not the foundation, to be the ground. Include parapet if you have parapet at the top of the roof. Usually, parapet will be, for example, like 1 meter, which is surrounding the roof. I'll put parapet like 1 meter. The terrain category is how much the building is facing the wind. So maybe it is in normal area, moderate, and strong. So if it's facing the sea or in a snow level, so you will take the strongest here. Okay, I will keep it normal in the normal. And you can see here, if you press on wind direction and exposure width modifying. Here the roof width, he took the width and the depth of the building. He took the width and the depth of each building. For diaphragm 3 have different widths and of course different depths because different slab. The typical are the same. For diaphragm ground floor is the same. When I see the widths and the depths, I mean plan view, and if you set extent diaphragm extent, we mean by the widths from here, from the two far points from here and the depth from here. So this is a modified extent. Okay, diaphragm extent. So I just want to show you what the wind load means. Okay, continue and return back to the load pattern. So we define the wind, and now we have EQX. The EQX direction is you would take it X plus eccentricity. Okay, we'll have the program calculated. I leave it by program calculated. Story range, of course, from the base to the roof. Here you have depending on the country. You are Norway, Portugal, Singapore, and others. So if I'm located in area like, for example, Malaysia, I'll go to code 8. So in Eurocode, if you open Eurocode here, you will see that Eurocode is Eurocode, okay. And you can see the ground type A, C, D, E. So I go to the tabs again. I use others. I will take it, for example, like the ground acceleration, big ground acceleration, like 3.25 G. Spectrum type 1 or 2. 1, of course, ground type B or C or D. I will take it C. And go back to Eurocode again. And we'll have, for C, we'll have 1.15. Here would be 1.15. And for the TB, 0.2. For TC, 0.6. And for TD equal to, this is lower bound factor beta always 0.2. If you search for this one, lower bound beta is equal to 0.2 from the code. So this is 0.2. The behavior factor which is related on the ductility level of the building can be 2, can be 3, can be 4, can be 5. So the ductility behavior, the DCM, for example, this is DCM BCL. So let's have this range DCM BCH. So in our case, I will put it and keep it as default. So this is how to assign the seismic elastic earthquake in this X direction. Okay, you can go to EQY. This add copy. Add new load again. Okay. Modify lateral load. Remove this all. This one, same, and change to other. 3.25. This one will be 40. This is true. So we define X, Y, and now we can define how we can run the analysis and check the elastic drift for earthquake, and we can check the elastic drift for the wind or the sway through the wind. So you can click on this button, run analysis, or you can go to analyze, set load cases to run. You have SIDL, you have wind load, you have EQX, you have EQI, you have dead load, you have light load. Okay, so you can run the analysis and make sure that the column the slabs have been assigned to load and run the mass. So maybe sometimes it takes time, but yeah, so the run analysis is finished. So this is the whole building now. This is the machine with displacement. So the first thing you should do is to check the sway to one load and to check the drift in New Jersey quick. You can go to tables, analysis result, structural output, joint output, displacement. You can go and find joint displacement here. Right click and show table. This is all the table through different cases. So filter this need for the wind. This is the wind in X and Y direction. Story. You can see, for example, for the roof, there is the top. Export the effect pixel. So all you need is to know displacement at the roof, which is maximum. Take max from here with 46 millimeter and take maximum for here 95 and take and so now we know the displacement, which is 46 millimeter in x direction and 95 millimeter in y direction. So now you can know the, 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 the form shape for the slab or for the building according to the wind load. So we see here the displacement in x direction. The maximum displacement due to wind load is 46.583 millimeter. However, in y directions is 95.925 millimeter. So what does that mean? These two values, how we can consider this to be okay or not? Let me show you from ETABS first how it behaves. If we go to show the form shape, okay, show the form shape, in case wind, step number 1, we have 1 or 2, 1 or 2. 1 means x direction, 2 means y direction. 1, you'll see the deformed shape. You see here the value is 39.481. You can see here 46.583 and here 46.583, which is 46.583. So this is the maximum displacement in the x direction. If you see in the y direction, be here 95.925, 95.925, here 76, here 76, and here 95.95. So is it correct or not? Is it allowable to be accepted this result or not? How you can know? In ACI code or most of the code, also in your code, they use the allowable displacement due to load equal to height divided by 500. So height divided by 500. In our case, we have 31.8. So the total height was 31,800 divided by 500 equal to how much? If you try to use your calculator, okay, it will be 318 divided by 500 to be 63.6. So allowable equal 63.6 millimeter, less than 95.95. No, so it is not accepted in the y direction. If you go to the x direction, you will see it is 46.583, which is less than 63. So in x direction, the wind load is accepted. However, in y direction, it's not accepted. So in this case, the building will not pass the sway if a wind happen in this direction, the y direction, it will suffer. So you need to check or to redesign or to add something to the building that accepts it. So the allowable equal to 63.6. This is the allowable. So in this scenario, in x is okay, in y is not okay. So we need this value to be less than this or equal to this. So we need to unlock the model, and we need to make the building resisting against the wind direction in this direction. So we need to put the stiffness, or we can add wall here. For example, I can add wall here in y direction. So may it solve the problem with all stories. We'll see if it will solve the problem. If I add wall here, it's 3.2 meter, and similarly add another wall here. Because I want to make it the same, 3.2 meter. So we add this wall to the whole building. So to see if check so just want to make it fixed. So I'm trying to say it fixed. Okay. Now we can go and see if the building can behave. Is it allowable? Yes or no? And the sway due to wind load. So it's on analysis. So let's see. So wind, x direction first. It is 39. You can see here also the maximum 39.208. So 39.28 correct in x direction. It is improved. Y direction is 65.06. 65.06. So it's okay now. It's okay to make it near to 63, but this is the solution now. The solution is to make it in this direction. So now we know how to solve the problem if you face any problem. So in this direction will improve in one direction. Maybe if we can rotate the columns here, or we can add drop beam surrounding the beam, surrounding the slab, so it will solve. So also you can see the display story response plot. On the story response plot, you can see also the behavior of the slab of the building. So you have the ground floor until the roof. You can change this to wind. You will see the values. You will see the value 39.208, and we will have here 39.28. We have 39.28. And step 2, we'll see here 65. Okay, here 2, here 65. So the problem is in the fifth floor. As usually, we take the wind load at the top. Okay, we take the wind load at the top, and you can have a new Excel sheet and a new data. Remove this one, don't save. You can have another Excel sheet, joint output, displacement, and joint displacement. Right click, show table, and you will see that you need to make filtration. You take for roof. I want to take here, right click, I need for the wind. I need for X direction, for example, and equal to 1. Okay, I take source step 1. So in X direction, you can see all the displacement 35, 37, 39, 35. So this is okay. In X direction, no problem. We can just change this to equal to apply filter. You can see in the roof have no problem. In the roof have no problem. So it can also considered as salt, because usually we take the sway at the top of the building. We take the sway, so in this case, this is okay. It's safe, and it is within the allowable range. Okay, so now you know how to check the sway. Now, if you want to go to check this, the earthquake or the story drift, go to story drifts, show table, and you'll have EQX, and you have the drift here. Okay, see the drift in X direction. You can file, export the current table to Excel. We open another sheet here. We will have this value in X direction. You can remove this one, linear static, this one. So we need to check the allowable of this value. You can multiply this by 0.7 and multiply it by 5.5. We can see the seismic load is within allowable. Why I multiply by 0.7 and 5.5? If you go to the code what say? The could say, if it is in UBC 97, which I'm familiar with, if you go to UBC 97, page number, if I'm not mistaken, you can go to page number 16. Yeah, you can see this equation. The maximum elastic displacement shall be computed as follow: 0.7 multiplied by R multiplied by the delta S. So the delta S is the story drift that we have. Calculate the story drift using delta M shall not exceed 0.025 times story height for the structure having fundamental period less than 0.7 seconds. However, for the structure having fundamental period of 0.7 seconds or greater, the calculated story drift shall not exceed 0.02 times the story height. We take 0.02. Okay, so I multiplied here 0.7 multiplied by delta S. So consider this as delta S. Okay, and consider this as 0.7, and R is 5.5, is this condition is response modification factor. You can see the response modification factor also in the code. You go to the code and go to the R values. The R values here. Yeah, this value we can take 5.5, depend on the building frame system. The building frame system, I will consider this as we have a building frame system. Okay, steel, concrete with shear wall. We take this one, concrete with shear wall, and take 5.5. Or you can take this issue also, moment resisting frame system, for the ordinary or intermediate 5.5. So based on what type of system you have, you can select the response modification factor. So again, go to page 16 and see use this equation for the checking the story drift. So you can write, I think, if you put this one, less than 0.02, comma, okay, comma, not okay, so the parentheses and say okay. So if you drag this, so all the values are okay, and okay, okay. So the story drift in X direction will have no problem. So the seismic assessment is passed for this building. You can close this one and save, and go to check EQY for the Y direction. The same procedure for EQY. Please export file, export the current table to Excel, and you can open the Excel sheet here. Make sure to take the values that you need. This is for Y direction, and you can delete this one. Equal this value times 0.7 times 5, here, 0.18. So this one in Y direction is more serious cases, but also this should be passed if this value less than 0.02, comma, say okay, and comma, say not okay, close the parentheses. So this one, all the values are okay in Y direction. So the same procedure have been applied to X and Y. So in the earthquake condition, the building will pass in the linear static assessment. If you go to the wind load, also it pass in X and Y, as you notice in the roof level, the building have been passed. So you can take this data and save it in your folder. So you can take this one for, you name it file, save as, you can make it file, save as story drift, you can name it story drift Y direction, and we'll save it as similar for X values and similar for Y values. So the allowable is 0.02 for the drift, seismic drift, and the allowable for the wind load is height over 500. So if you go to check this one, set services. Okay, everything is run and finished. So now we know how to define, know how to make the seismic assessment and for the wind load and for the seismic load. Now we need to define something called load combination. We unlock this one, go to define load combinations, add a new combo, and we start adding a combination. Go to ACI code. ACI code. ACI code. Which page? Page 60. Page 60. You will see this load combination that should be taken into consideration. But you should also go to this equation 5.131, 5.1b. Based on the code, you can add the load combination. Go to load combination. You can use add default design combination, which I don't prefer to do this because I want to insert envelope and too many things. So for combination number one, I will consider that load 1.4, that load. I will consider the SIDL as well as 1.4 that load. Add the new combination. Combination number two will be 1.2 dead load and superimpose also 1.2 dead load. And dead load will be 1.6 load, live load. And combination number three will be add a new combo which is 1.2 dead plus SIDL 1.2 plus live load 1.6 plus wind load 1. So this is for combination C wind load 1. You can make also a copy of this combination. I mean this one is -1 and then combination 4. And you can make now another combination at new combo, or you can make a copy also because I need to change this to 1.6 wind load 5. I'll copy as well, change this to -6 6 mistaken, yeah. And now we need to go to prepare some envelopes equation. I will name it EX envelope this way, EX envelope. So in EX envelope, I will add EQX in this direction. Okay, and I think we should add also okay for this one we can add defined load pattern. We can add EQX also define the third load. You can add it once in positive, one in negative. So I can make EQS plus define load. I can put this equal y define load. So now I will put another equation EQX minus add a new load. Same. This one. Same procedure. And we go to others. You can go to Eurocode again. Remember cell type C. This one 0.5, I guess. Take this one 1.5. Take this one 0.2. I will take this one 0.6, as well as this one 2, 0.2, and 2. So this is for EQX negative. I want to add EY negative to be a load, modify the term load. So remove all these and keep UY negative. Others 0.25, and you can change this to 1.15, 5, and you can change this to 0.2, 6, 2, and the flip will have it. So this one same, this one the same, this one the same, this one also white. So in this case, we define the all letter load, define again the load combination, continue the envelope equal x or e x envelope equal x1 equal x and equal x negative. Okay, and you can also add another copy equal x envelope, but our AY envelope, sorry. So too many combinations, we need to be careful. Equal positive, equal negative, plus. You can add now another combination, which is linear EX XY, which is EX envelope and EX EY envelope. EX Y. Just the name is a times of EX XY. So now continue combination. So add group, add new combo, which will be 1.2 dead load, 1.2 superimpose dead load. And you can go to one live load, and you can go to this one, the XY. So I take everything here, the both input of X and Y in one combination. So we consider it as one. Okay. Add copy of these. The same I'll change this to -1. -1. And copy. This will be EX minus Y. 1. And copy again. This will be condition 10. This one should be -1. Okay, so we have now 10 combination. Not finished yet. We can add more. Combination number 11, which is 0.9 load and 0.9 boosted load and 1.6 wind. And copy. So 12 minus 1.6. Not finished yet. 3.9 SITL 9 EX minus Y X plus Y for start Y plus copy minus copy should be yes minus y 1 2 add copy 16 minus 1. So now we define all the load combination. You can see and follow this step 1.2, 1.6 live load, 1.21 0.9 load, 1 wind load, earthquake will be enveloped. That's why I asked you to follow this one or this one 5.31D, search for this 5.3.1. You can see here the 1.6W, the 1, the 0.5 equate, so I take the maximum here. So that's why I always asking you to read, don't follow you follow, of course, you can follow the combinations, but the combinations is very general here. So you should do like this. Combination number 1, okay, 1.4 that where is it? This one. 1.2 plus 1.6, we don't have snow or roof, so we'll keep this. Here maybe you can add 0.5 wind load, but we have 1.6 wind load, so I can add 1.6 wind load maybe here. This is one. So this is all the combinations. The AX envelope here, make sure that you X plus minus envelope, Y envelope, Y minus Y. So now we define all the load combinations for this model. Also, now we need to check something called for if you are going, because next stage will be design. Next stage will be show you define properties section. This one show modifier. This one can be changed. If you go to design in elastic assessment, everything here will change. For the columns will be 0.7 maybe, and the inertia 0.7, and the inertia here is 0.7. Okay, so we'll not make it now. Now we need to check. So we'll show you a few options. Tabs for displacement, structural weight, display, store response plot. You can see from here the combinations X, direction, 94 millimeter, displacement at the drift. Okay, equals negative 101, minus envelope. See all it's weight. And also show displacement here. Displacement here. And you can see the source here. You can take the source here. Each level. We have this here 7442. This is the FB. The FB. Next connection. One connection which is 908. PQ axle, which is the 742. It's 908. So this is this year. This study. You can go see also the period of this building. How to know the period, the fundamental period. Fundamental period represents its small shape, the model. This point. Number one, see, have the period here 1.008. In x direction, in y direction, we have it 8.85. Torsion base, we have it 0.82. Can still show the building mod shape until 12. See here the deformed shape, mod shape 12. So we go to see the fundamental period T1, which is equal to 1.008, which means we see we compared by 0.02 because it's mentioned that for the structure having fundamental period of 0.7 seconds or greater, it should go to 0.02 for the drift. Okay, so this is the drift. You can see also the reaction, it's called the support reaction. If you want to go to combination 2, for example, which is considered as the ultimate, 1.2 load, 1.6 live load, you can see the reaction in the plan view also. Base, you can see here upset. Okay. Tabulated maybe. 1517 km. Combination 2. You can see as well the display, the moment diagram. Column. This is the moment diagram for the column. You can see select object type columns. You choose object only. You can see the moment right click with the shear, and there is a moment for the column based on the combination number 2. Go to envelope combination. So based on the combination you can design. And here combination number 1 not only. If you want to see also axial differences, see the axial force from the column, from the base to the roof. You see this one, force 1, axial force is force 3, force 6. This is axial forces. So if you select the object on show object percentages. So now we know the drift and the sway are okay. We define the load combination. Now we need to know the deflection of the slab. In ETABS, deflection of the slab is not is difficult to be read. You can see display on form shape. see spade form shape. This one combination 2. So I want to know the form shape for the slab. Go to this case and put combination 2, displacement Z. You'll see 10 millimeter here. Combination, but this one for combination 2, which is 1.2 dead load and 1.6 light load. We need 1 dead load plus 1 light load. So look, define combination 17, which is dead load 2, which is 1, SITL 1, light load 1. This one is for short-term reflection. So you can run the analysis and wait for the form shape for the slab. See the difference? Now if you go to the form shape, we need to know the combination 17, which is that little slide load. Let's say use it. See now it's 8.0 something millimeter for the short-term reflection for the serviceability combination. Make it in a plan view. You can see the deformed shape should be here, which is 8.026. Okay, so this is the form shape for the short-term reflection. I prefer to use safe software. So how to use this software? Okay, unlock, file, export story as safe, go to 8.4, select load cases, that look like it's superimposed enough, select combination number 17, okay, and export floor loads only. Name this one reflection, typical stories. So I go to save. You will see save 2000, save, sorry, save 2014 go to 5, import, save F2K5, and reflection for typical stories. So this is a slab, will be the same, like ETABS, and right click, left node, you see the live load and the dead load, 3.5 by 1.2, which is the same as in ETABS. You can go to 3D also, you can see this one. Okay, XY. So now we need to define, we have the load combination here, combination 17. We can define the load cases. As I see, I have this information. Safe to version 12, long-term reflection calculation example. We'll have case 1, A case 1, A case 2, A case 3. So first of all, we need to define case 1, which is the self-weight, but superimpose that load, plus this factor with times live load, which is the concrete modulus factor. So it should be static and non-linear crack. So it's okay, go to save, define, same as ETABS, the same concept, define load combination, or sorry, define load cases, add a new case, add a new case, okay, this is case number 1. Case number 1 would be set so you are now this is from save 2000 long-term reflection into case number 1. Case number 1 will be self weight superimpose the load and life load into dead load 1, life load 1, and superimpose static 1, non-linear static. This is case 1. And copy case 2 will be self weight, dead load, live load 0.3. Here we have non-linear crack 0.3, and change this one to case 2. And copy for case 3. The non-linear long-term reflection. The equation in case 3 will be same 0.3 but non-linear crack section. And when you define case 1, case 2, case 3, you can go back and see the load combination for the dead load and load combination plus case 1 plus case 2 plus case 3. You should go to load combination, define load combination combo, dead load, live load, so dead load, and equation 1, 2, 3, case 1 plus case 3 minus case 2. Case 1 plus case 3 minus case 2. This one should be service time, sex ultimate, that copy long-term deflection C1 plus C3 plus C2 minus that load. This will be for LTD, long-term deflection. This one is 3, this one will be load, this one should be okay. So should be dead only. Dead. Minus 1. That's one here. So what you have to do is to run the analysis for this story, for this typical story. Can limit long-term reflection for slab this will take time. You can see now this finished analysis. You can see the deformed shape. Go to the load combination here. Go to combination long-term reflection, which is important for us. Minus. You can see here's a minimum minus 19 millimeter. You can see here also the same location as shown in ETABS. Minus 19 minus 20. So in 3D, see the deformed shape. This is a deformed shape for this stuff. Okay. So this area should be all normal. So also another condition, you know, because it is flat slab, you know, the punching could happen, right? You can go to select punching, which is this one, show punching shape design. You can see both of the columns have been passing. This one need to be double check 1.5396, which is exceeding based on SI code. The punching is more than 1 because you can see the maximum design shear capacity stress is 1.9 and the concrete shear stress capacity is 1.26. If you divide 1.95 by 1.26, you'll get 1.54. In this case, you need to add like a shear studs here and a can shear studs here, and that's it with most of the columns is passing. Similarly for this one, is I think 1.31. Okay, so for the punching shear reinforcement is passed, and you can also check the deflection for the short-term deflection. This is combination 7. Also would be 4 millimeter, 4.5 millimeter. This is 4 millimeter for the short-term deflection, and for the long-term deflection will be 19 millimeter or almost 20 millimeter. So to solve this issue, go to my calculator. The maximum span is 6,000 millimeter. Divide if 97 to 180 maybe. So the allowable may be 21 millimeter, which is within allowable. Or you can go to SI code and check the deflection, which is page 402 from the deflection. So it's L by 240. Okay, I divide by 280 here. So 6,000 divided by 240. So we have 25 millimeter allowable, which is more than 19 millimeters. So our deflection, the floor type is safe against deflection in the long term and under the short term deflection. So yeah, you can go return back to ETABS. So now we know everything this way, and we know the drift. Also, there's something you guys need to know is if you want to go to make it to change the stiffness modifier, as the code say, you can go to define frame section, go to this one, as I say, you can change the modifiers here 0.7 to 0.7 to 0.7 based on the code. The code say on page number 74. You can see the moment of inertia of cross section perfect for elastic acid factor. Load 0.7, 0.7, or you can cross section area 1. I use for this one 1 okay? AG means across without cracked section. So now we know the displacement, we know the sway. We can know the reinforcement of each column. Is the column pass or not? How to do this? Go to define the combination for the ultimate case. Okay, define the information for the ultimate case, which is for the gravity load system only. 1 point dead load, 1 point dead load, 1.6 live load, and you can check the capacity of the building or capacity of the columns. Run the analysis. So you can see here displacement also. Displacement. What I want to show you is capacity of the columns, pass or not. So if you want to view, select object type, columns, view, show selected object only, and you have the column now, right? The columns. Design from here, we have design by using ACI code. This is the number of interaction for the curves, you know, the PM curve, which is 24. So this is all the categories or the coefficients used for ACI code for designing column. And you can go to this one. I want to go to select design combination. Our combination is combination 2 for the dead load and live load for the gravity load system. And we have the rest here with seismic and earthquake, which is later we can explain this, or it's not available for your session. Combination 2, and you can press on this complete design. You can see the design is faster than the manual design. You can see this color is this pinky color. This means that all the columns are safe, and he can show you this value 2100 millimeter square. This means that the area of the steel rebars is 2100 millimeter square. This one 2400. Remember when we did this, we go to define frame section, define properties, and we add the rebars, these rebars. Remember this? So here 8 times 3 means 24. So we have minimum reinforcement rebars here. Minimum reinforcement rebars. See, 300 times 800 we have. The combination 2 is, you can go for details. You will see the design. First floor C27, section is 300 800. Sway special. You will modify elasticity, steel bars. So you will see the axial load, the minor moment, ultimate major moment, and percentage ratio is 1%. See, the percentage rebar is 1%, same like the rebar area is 2400, and everything is correct. So also you can go to this one and select display design info. I want to see the rebar percentage. Okay. You will see the rebar percentage is 1%, right? 1%, 1%. So this is the rebar percentage. So identify any failure, no failure, no failure. Column beam capacity, there's no beam capacity, so rebar percentage is not good. So reinforcing is also good, which is the minimum. So torsion as well is nothing. So we are in a good way. We have the reinforcement area and we have the rebar percentage reinforcement area, which is 1%. Okay. Okay, so in this case, you can go and design data. You have to go to design and design forces. Okay, concrete frame design, concrete frame summary, concrete column, design summary. Right click, show table. You will see, and you can export this one. Need, for example, I want to use section 300, 700. Okay, this one, and I need usually take the base, the ground floor level, which is the maximum load of design will be at the bottom, right? Okay, I need this section for 300, 700. We have all status design output. Status is no message, no failure. We have error still minimum, error still provided or required. So no error message, so we are on the safe side here. Okay, can change this one to 1500 and also the same error still. Okay, concrete column PMM value, big beam, see this. You will see here the axial load and the major moment and the minor moment and the reinforcement or the PMM reinforcement ratio, which is 1% of the whole structure at the ground level. So yeah, design forces here, show table as well. You can see the P axial load, you can see the minor shear force, major shear force, the torsion zero. This will explain about the detailing in the next session. Okay, this is report. You can find the project report or summary report. Want to go to project report, this will take time. You can see this is all the report you can get. And now, chapter 4. This is the report you can download. This one, project report. So this is a summary of our building report. You can take it and read in details what do you need. So now we know how to design. We know the capacity ratio for the columns. We know the reinforcement, how much we need. We know the sway. We know the drift. We know which code to use. So we know the deflection for the slab. We know the short term and long term deflection of the slab. Because it's still saving. And we know how to define the load combinations as well. We have the table of content, material, what is frame property definitions? So this is the summary of the report, which can help you to go and write something. So the important things is to know the short deflection, long-term deflection, the sway, the drift, and the axial forces on the columns. And if we have beam, we can make it also the beam, depending on what they come with the beam. Okay. Move back to this one. Yes. So we know from B tabs here, and we know from 6 deflection for safe from here, and we have this note send it to you also. Safe for designing the slab in details and find the foundation as well if you have. So that's all for this session. And the next session will provide more details about the design for the slab, for the columns, about the nonlinear time history analysis, nonlinear static analysis like this one. You have to find the response spectrum. Okay, you can calculate function. So you can define here time history analysis as well from phi function. You can add the time history analysis for this one and study the displacement for the ground motions. And this is for the design. And you can see the stresses also for the slab and the moment of the slab. You can see we need M22, which is moment in y direction, M11 moment in x direction. We have the combination 2, go to M22. You see the moment here. Here the yellow for combination 2 in y direction. You can see it's really pure. The moment positive and negative. It's the combination. Combination movement diagram resulted movement diagram. So each support is having its moment. So negative moment with positive moment, negative moment. So here support column negative, negative, positive, negative. You can see the scale here. The green part is the positive and the yellow part is the negative. Thank you so much and see you in the next session and have a nice day. Goodbye.